In free time, you please do it. Okay. So now next one, de Broglie hypothesis. Okay. What is this de Broglie hypothesis? In 1924, this is the famous scientist de Broglie. Okay. In 1924, he proposed dual nature of matter. What is the dual nature of matter? Okay. Dual nature of matter. Okay. Before that, what is matter? What is matter? What do you know about matter? What is the matter? Matter means what?
Matter is
Which
anything that
occupies
occupies some
space.
space.
Uh,
Example, liquid, water,
uh,
liquid, solid, and gas.
okay, what did you say? First sentence I could not hear.
Matter has
And
some mass and it can move from one place to another place.
Yeah, okay, good. And another person also saying,
anything that occupies some space.
yeah, okay, good, very good. Both are correct answers only. Okay, matter means just any particle or anything. It should have some mass and it should occupy some space in a some place in a space, or you can say anything. So if you take any suppose if you take any cricket ball or something ball, it is having some mass, right? That is matter. Okay, or anything, it should have mass. Okay, it should have mass. That is the matter means. Okay, and if you keep this matter, or if you keep a cricket ball or something else, it will occupy some space, right? That is the matter only. Okay, dual nature means what we know uh, from the light. Okay, when you observe light. Okay, we have studied particle nature and wave nature. Particle and wave nature, these are two natures: particle nature and wave nature. What we have studied just before, light is sometimes behaves as a particle and sometimes wave, depending on circumstance. Okay, suppose if you take, what is the suppose photoelectric effect and Compton effect. What we have considered, photon light is Compton effect. Light is it wave or particle? In photoelectric effect, Compton effect,
Uh,
wave. Anybody? In
It
photoelectric
has
effect,
both nature.
yeah, actually, light is having both nature, but when you explain photoelectric effect, Compton effect, we have taken as a particle behavior. Okay, particle behavior, particle nature. Okay, why? Because see, when nucleus is there, right? Here electrons are revolving. Electron means it's a particle, right? Electron is a some particle. Or okay, if you incident some light here, this okay, it's gone. Okay, so this is electron. So this wave should not make collision with electron particle. So always particle will make collision with particle only, right? Wave will make wave only, right? That is like if you see, if any example in outside, two collision between two bikes, here also, where this light should be particle only, then only it is explained correctly. So in photoelectric effect also, what Einstein proposed, light is a teeny particles. Okay, teeny particles. And this light also, energy also quantized. What he proposed, quantized and discrete. This teeny particle, what he named it, this teeny particle, this quantized discrete energy packets, photon, right?
sir,
Photon, right?
Yes,
Ah,
sir.
yeah. So what Einstein, while explaining photoelectric effect, Einstein, what he proposed, light also, it travels, propagate as a energy packet, small energy packets are teeny particles. This energy also quantized and discrete. These quantized discrete energy packets, what he called photon. Now this is the in case of light. Before that, when we studied this Planck's radiation law, okay, Planck's radiation law, okay, what he proposed, when radiation interacts with matter, okay, when interacts with matter, radiation interacts with matter, energy exchange happens in the form of quanta, or in the quanta or quantum, you can say quanta. And this energy also discrete and quantized also. Okay, quantized. Planck's proposed, okay, just he took any radiation, okay, any radiation. When radiation interacts with matter, it releases energy as a in the form of discrete amounts and quantized. These discrete amount is called as a quanta, okay, that is in the form of h nu, right, in the form of n h nu, okay. First what he, this is in 1900 something, 19, this is 1913 something, something like that, okay. So when once Planck's proposed this thing, when energy exchange between radiation and matter, it is a releases as a amounts of quanta or amounts of h nu, eh nu, or E is equal to E in the form of h nu. Okay. After that, this same concept implemented to light. Okay. This same concept, what photo Einstein implemented to the Einstein implemented the same concept to light also. Light also it behaves as a wave and particle. This light also propagate in a teeny particles or energy small energy packets. These energy packets he called photon, and here he called quanta. Okay, the name is different but same thing. Okay, this is the radiation matter. This is light in case of light. Here also, here what de Broglie this already proposed this. Things. Okay, light when we observe photoelectric effect and photoelectric effect and Compton effect, we have taken light as a particle nature. Okay, so when you take interference, okay, when you take interference and diffraction, okay, when you take interference and diffraction, light is a wave nature. Okay, they consider here in interference and diffraction, Newton's interference. I think you have gone through in intermediate. Okay, this is light is a particle wave in interference and diffraction. Okay, but in photoelectric Compton, just few days back we have studied these two concepts. Okay, here light is a particle. Okay, so light is sometimes is behaving as a particle, sometimes wave. So it is having dual nature. Like here also what de Broglie proposed. Now you got right in case of light you understood, right? In case of light, dual nature of light you understood, right? Now we will see de Broglie matter waves. What is matter waves and what he proposed, we will see. Okay, matter waves means mainly he proposed dual nature of material particle. Okay, material particle or dual nature of matter. Okay, dual nature of what he proposed, dual nature of material particle. Okay, material particle or matter you can say. Okay, matter also you can say. So here, so every moving microscopic particle, moving, what is the de Broglie hypothesis means? Moving micro particle. Micro means, what is the micro? It's
Micro
order
means
of
small, macro means
yeah,
small. Big,
yeah. Micro means it is a range of
small.
atomic level, atomic very small. Okay,
Yes, sir.
atomic range. Okay, moving micro particle is associated with a wave. Okay, associated with a wave, associated with a wave. That is E proposed or hypothesis. De Broglie hypothesis is any moving micro particle is associated with a wave. Okay, or you can say, or you can write, okay, wave associated with a particle, a wave associated, you can write anything. Okay, associated with a wave, sorry, particle, or you can write wave is associated with a particle, he called as a de Broglie wave or matter waves. Okay, matter wave means de Broglie wave or matter wave, matter wave. Okay, this is he proposed. Okay, any material particle means the particle having some mass and it is in motion. Okay, that particle always associate with a wave, that is the matter wave. Okay, is it clear now? Okay, suppose wave means, you know, right? Wave, what is the wave? What is the wave? You are seeing many places wave. What you can define? Okay, it's just wave means it's a spread out. Okay, wave means what? It's a spread out or
Which have
any this any disturbance in a space, any disturbance in a space, or any, it is a spread out of Okay, in the spread out in a space. Suppose if you take a water, if you throw a one stone here, okay, you will observe some waves, right? Waves like this. Okay, particle means it will move a particle type, it will move. Okay, okay, this is the particle aspect, this is the wave nature. Okay, so here also, if you take cricket ball, you are throwing a cricket ball, right? Suppose you have cricket ball, this cricket, just this is example, not this one. Okay, if you throw cricket ball, suppose it is going like this way, okay, like this way. Okay, so it is having some mass and it is behaving a wave, right? It's behaving like a wave. That is the matter wave. The example is just I'm explaining this one. Okay, so this is macroscopic body, just I'm explaining analogy. This is just analogy. Okay, you remember this one, don't write in the exam. Okay, because cricket ball is a macroscopic body. Okay, it is not microscopic. So if you throw cricket ball, it is having some mass, and it is, if it is hit the, if you throw anywhere on the ground, it will flow like this, right? Isn't it? Have you observed or not? Cricket ball, any ball, something like that. Have you seen or no? Hello, did you see or no? క్రికెట్ బాల్,
No, sir.
Yes, sir.
Seen,
క్రికెట్
sir.
క్రికెట్ బాల్ ఆడుతుంటే మనం నేల మీద కొట్టినప్పుడు అది ఎట్లా పోతుంది? కొంచెం వేవ్ టైప్ లో వెళ్తుందా లేదా?
Yes, sir.
Yes, sir.
Yeah, same thing also. It is a cricket ball means that is macroscopic. We cannot apply to material matter waves, but just analogy. If you take analogy, it cricket ball has is having some mass, and if you throw it out, it will flow. It will propagate like a wave. That is the just example. Okay, don't write this in exam. Okay, like that also, every material particle having, it is showing some particle nature and also wave nature. That is the de Broglie hypothesis. Okay, that is it clear now, everyone? What is the de Broglie hypothesis? Every moving microparticle is associated with a wave. Every moving microparticle is associated with a wave. Okay, these waves, what we are calling de Broglie waves or matter waves. Okay, we have seen light just before we understood light. Okay, or you can say light now in matter waves. Okay, light and matter waves. The difference you got it right here. What is the matter waves? What is the light waves? Okay, what is the, do you understood this one? So light is a
Yes, sir.
matter. Light doesn't have mass, right? It doesn't have mass, but material, matter waves means, matter means some particle, it is having mass. Okay, the difference is that one. Okay, matter waves, it behaves as sometimes a like particle aspects and sometimes a wave nature. Okay, that is the matter de Broglie hypothesis. Okay, you got it right. So, and the wavelength of this matter waves is, he derived the expression lambda by h by p. P is the momentum of a particle. Okay, momentum of a particle. Suppose if you take any particle, this particle is moving like wave, moving like wave. So this is whole as a matter wave. Okay, the wavelength of matter wave is equal to h by p. P is the momentum of what? Momentum of what? Particle or wave? Sorry. Momentum of what? Particle or wave?
Particle.
Okay, just a second, please. So, what are the characteristics of particle? So, how you identify particle? Particle or proper particle? What are the characteristics of particle? What are the characteristics of wave? So, what here? Particle means what should this have? Mass, sorry, mass and velocity and momentum, momentum and energy, momentum and energy. So
Energy.
wave, yeah, wave means frequency, wavelength and phase, amplitude and intensity. Okay, How you will characterize the wave and particle? So particle means it should have mass, velocity, momentum, energy. Okay, wave means it should characterized by frequency, wavelength, phase or amplitude or intensity. Okay, these are the how you will distinguish particle and wave. Okay, and the difference between particle and wave. Okay, now he derived the expression lambda is called h by p. Lambda is called h by p. This is the wavelength of matter waves, and the p is the momentum of momentum of particle. Okay, or you can write this is h by momentum is called what, m into v, right? Mass into velocity, right? You can write, right? So now we will derive this expression. Okay, now we will derive this expression. Is this clear up to now? What is the,
Yes, sir.
so just light also behaves as a particle and wave. If you take photoelectric effect, Compton effect, there we consider particle. Okay, but if you take interference and diffraction, we taken it is a wave. Okay, when in 1900 Planck proposed when radiation interacts with matter, releases energy in the form of quanta or discrete amounts, that is called nh nu. Okay, for photoelectric effect, this Einstein also proposed same concept applied to light also. Light also propagate tiny as a small energy packets or tiny particles. These energy packets he called a photon. Okay, this is also quantized and discrete amount. Okay, this is a difference. Okay, after that in 1924 de Broglie came, he proposed dual nature of material particle or dual nature of matter waves, also dual nature of matter wave. Okay, material particle means it should have some mass and this thing. Okay, every moving microparticle is associated with a wave. Every moving microparticle is associated with a wave. Okay, see, for that he proposed lambda is equal to h by p. Suppose the particle always should have mass and velocity, otherwise the what is the lambda, it will, we cannot define, right? Suppose particle mass is 0, what is the lambda? Infinity, right? Suppose velocity is 0, what is the lambda? It is infinity. So it is, we cannot define if the microparticle is doesn't have mass and velocity. Okay, it is the, from this expression we can conclude always microparticle should have mass and velocity, then only we can estimate the wavelength of the matter waves. So matter waves means what? Every any material particle, it is showing a wave or associated with a wave, that is the matter waves. Okay, now we will derive the expression, right? Is this clear, right?
Yes, sir.
Okay, this expression, this de Broglie hypothesis is very, very important, but very easy. Okay, very important and very easy. So what is the Planck, from the Planck's radiation law? Planck's radiation law, what is the energy? What is the expression for energy? Just now also we have discussed. What is the expression for energy? E is equal to how the energy release, uh, how the energy released when radiation interacts with matter. Okay, that is h nu, right? In terms of h nu, right? Isn't it?
Yes, sir.
Okay, this is one expression. So next one, Einstein energy mass relation. What is the Einstein's energy mass relation?
MC square.
E is equal to
Yeah,
mc square.
very good. Okay, energy mass relation. Okay, you can write here energy mass E is equal to mc square, right? So expression 1 and 2, just this is also energy, this is also energy, just you equal 1 to 2. Okay, then we get h nu is equal to mc square. Okay, here nu is equal to what we can write? Frequency
By lambda.
c by lambda, that's good. Okay, c by lambda is equal to mc square. Here 1c will get cancelled out, and you bring it this lambda right hand side, lambda is equal h by mc. Okay, h by mc. So this is lambda is equal to h by mc we got. Okay, this is in case of light, so but we want material particle, right? Matter waves, this is in case of light we have derived. for a material particle or material particle. Okay, material particle. If you consider a material particle, but we want for material particle or matter waves, right? So it is having some mass and velocity, some velocity v. Okay, so the lambda is, you can just rewrite this one, mass of particle, and in here light velocity is there. Just you replace with some velocity. Okay, that is the wavelength for the matter waves. Okay, this is the expression for matter waves, wavelength of the matter waves. Okay, or you can write lambda is equal to h by mv, means p, right? H by mv is equal to, you can write p. Okay, is this easy or difficult? But this is very, very important. Okay, just first one, we know Planck's radiation law is equal to h nu, right? Is equal to h nu. This expression we know. After that, energy mass relation, that is E is equal to mc square. Just equal these two terms and we will get the lambda is equal to h by mc. This is expression in case of light, but we are going to derive the expression for material particle or matter waves. Okay, for that, suppose if you have a material particle, it has some mass and it has some velocity. Okay, it has some velocity, not light velocity. So in this expression, you replace light velocity with uh, particle velocity. Okay, particle velocity, that is lambda is equal to h by mv, or lambda is equal to h by p. This is the expression for wavelength of the de Broglie waves. Okay, this is okay. Up to now, is it clear? You can derive, right, directly without seeing.
Yes,
Can
sir.
you, can you derive?
Yes, sir.
Just only two expression, from there equal the two expression, you will get the lambda is equal to h by p. Okay, now this is the famous expression for wavelength of a matter waves, wavelength of matter waves. Next we will solve in three special cases. One, suppose wavelength, this wavelength in terms of wavelength, this wavelength, de Broglie wavelength, you can write de Broglie wavelength in terms of kinetic energy, in terms of kinetic energy. Okay, case, this is case one. Okay, can write case one. Okay, case one. Okay, I will take new page. Okay, okay, case one in terms of, in terms of kinetic energy. Okay, what is the kinetic energy generally? What we know of mv square, isn't it?
Half
Half
MV
mv
square.
square.
Okay, now we know lambda is equal to h by mv or h by p, right? Now we have to replace this mv using this expression. Okay, so here ke is equal of, here I am dividing with m and multiplying. So here m square v square, right? From this expression we can write m square v square is equal to 2m into ke, or you can write e also. Is it right? Okay, after that mv is equal to 2m ke under root, right? So you substitute this expression here. Okay, you simply substitute this one. Lambda is equal h by 2m ke. Okay, 2m ke. This is the de Broglie wavelength in terms of kinetic energy. In terms of kinetic energy. Okay. Suppose if you know kinetic energy of any material particle, you can estimate lambda. You can estimate wavelength of a material particle. Okay, is this clear? Just we rewrite this expression. Okay, we know kinetic energy. From there, we replace this expression. Momentum we replaced. Isn't it? Is it clear?
Yes, sir.
If you know kinetic energy of any material particle, you can estimate the de Broglie wavelength. Okay, that is the expression, meaning the significance of this expression is, the significance of this expression is, if you know kinetic energy of any material particle, you can estimate the wavelength of de Broglie waves. Okay, now second one in terms of case 2. Okay, here case 2 in terms of, in terms of uh, potential energy, in terms of potential energy. Okay, suppose if you take a charged particle. Okay, charged particle. Okay, charged particle, and it is having some charge q, and potential energy we are applying some potential energy v. So the in case of a so kinetic energy is equal to what? So in photoelectric effect, what you have written? Q into V, right? Q into V. Suppose here plate is there. Here electrons are ejected. These electrons are moved to this plate by we are applying some potential energy. Here we have written kinetic energy is equal to the potential energy, right? By applying some potential only, these electrons getting energy, some energy, thermokinetic energy. Then these are electrons are accelerating and moving to this plate. Here also, if any charged particle is there, here for the charged particle, this kinetic energy is always equal to the potential energy. Okay. Here also you can write mv square is equal q to q into v. So we want m square v square, right? M square v square. Here multiplying here m 2m q into v, 2m q into v. So here mv is equal to, you can write 2m q into v under root. Okay. Then again you substitute in our lambda expression. Lambda is equal h by 2m q into v. 2m q into v. Okay. Then this is the expression for matter waves in case of a charged particle. In case of charged particle, suppose electron is there. Electron also having some mass and velocity, right? In case of any charged particle, the expression is for matter waves lambda is equal to h by 2m into qv. Suppose if you know potential energy, you can estimate the lambda. If you know potential energy of any material particle, you can estimate the lambda using this expression. Okay, that is the significance of this expression. Suppose if you take electron, for the case of electron, lambda is equal, just I am simplifying this expression, 12 point, just a second, what is this one? 12 point, you can also calculate this one, 12.26 by root V, this is angstroms. Okay, so how we got this 12.26? Here Q means electron charge, we know that is 1.6 into 10 power 19 minus 19 coulombs, and mass also we know 10 power minus 31 kg, 9.1 into. Okay, and H also we know. You substitute these values here, then we don't know potential energy. Just we got the we simplified this expression, nothing here. Okay, just we simplified by substituting the electron charge, mass, and Planck constant value. Okay, in case of electron, the matter wave velocity wavelength of the matter waves is 12.26 by root v. V is the potential energy, and it will comes into angstrom. Okay, it will comes into angstrom. Okay, is this clear, everyone?
Yes, sir.
Yes,
Just
sir.
if you need charged particle also, suppose you have a charged particle, it is having some potential energy. Okay, that potential energy is always equal to the kinetic energy. Using that expression, we have derived the expression for de Broglie waves. Okay, that is lambda is equal to 12.26 by root v. The v is the potential of any particle. Potential of any particle, any charged particle, or you can write any charged particle. Okay, right? So now this is the expression. One more we have, that is in terms of temperature, in terms of case 3. Okay, case 3 is in term, just time is up. Just I will take only 1 minute. Okay, is this okay? Just I will take 1 minute, please. So in terms of temperature, okay, if you know temperature also, suppose in a thermally, if any particle is there, the kinetic energy of any particle is 3 by 2 k into t. K is the Boltzmann constant, T is the temperature. This is equal to some kinetic energy. Okay, this is also kinetic energy of a particle if you apply some temperature. Okay, if in terms of temperature, kinetic energy is given by this expression. Okay, from there also you can write here K is equal to half mv square, right? Half mv square. These two will cancel out. Mv square is equal 3 kt, right? 3 kt. So we want mv, I will write 3m kt, right? I will write, can I write like this? Just I am multiplying m both side. Here I am multiplying m both side and just taking out mv out. Okay, from there lambda is equal to h by 3m kb into t. This is the expression in terms of temperature. In terms of temperature. So if you know temperature also, you can estimate the, because of temperature also particle get accelerated, right? Because of temperature also any some particle will get, any particle will get some thermal energy, right? Thermal kinetic energy, right? Isn't it? Isn't it? Suppose if you
Yes,
have
sir.
if you have particle, you are heating this particle, you are giving some temperature to this particle, so this particle it will move to and fro or somewhere else, right? So by moving means it is getting some kinetic energy, isn't it? So that is
Yes.
Yes,
the,
sir.
so finally what we have derived today, lambda is equal to the matter wavelength of matter waves. Wavelength of matter wave is lambda is equal to h by mv, or that is you can write h by p. Okay, h by p. And second one in terms of kinetic energy 2m ke. In terms of kinetic energy we have derived expression 2m ke. And in terms of charged part
Potential energy.
potential 2m q into v, q into v, or in case of electrons this is equal to 12.26 by root v Armstrong. Okay, and third one is in terms
In
of
terms of
temperature.
temperature.
Okay, 3m k into t. This is kb I written, that is Boltzmann constant. Okay, this we have derived in this class. This is case 1, case 2, and this is case 3. Okay, just go through this expression. It is very easy. Just kinetic energy you have to write in terms of lambda. Okay, that's it. Okay, now I am closing the class already. It's late. Okay, thank you for. Okay.